So let's solve one more question. Show that the function f given by f of x is equal to x square plus 2, where x is not equal to 0, and f of x is equal to 3 if x is equal to 0, is not continuous at x equal to 0. Now here the function f of x is defined as x square plus 2 when x is not equal to 0 and 3 when x is equal to 0. And we have to check whether this function is continuous at x equal to 0. So first of all, let's check whether this function is defined at the point 0. We are given that the f of 0 is equal to 3. So that means the value of the given function at 0 is equal to 3. And now let's find the limit of this function at 0. Now limit of f of x when x approaches 0 is equal to, now the value of the function f of x when x is not equal to 0 is x square plus 2. So in place of f of x we can write x square plus 2. So the limit becomes limit x approaches 0 x square plus 2. So when x approaches 0, then x square, which is equal to x into x, will also approach to 0. So that means the value of limit is equal to 0 plus 2, and which is equal to 2. So the limit of the function fx when x approaches 0 is equal to 2. But the value of the function f of x at x equal to 0 is 3. So that means the limit of the function f of x when x approaches 0 is not equal to the value of the function f at 0. And as per the definition of continuous function, the given function is continuous at a point if and only the value of the function at the given point is equal to the limit of the function at given point. And here, because this is not the case, as the limit is not equal to the value of the function, so that means the given function is not continuous function at x equal to 0. Now let's do one more example. Prove that the identity function on real number given by f of x is equal to x is continuous at every real number. Now from the definition of identity function, you know it very well that identity function is a function in which the value of the function at a given point is equal to the point itself. Or in other words, if c is a point where c is a real number, then f of c is equal to c. So that means the identity function is defined at every point on real number and its value at the point c is equal to c. Now let's find the limit of this function f of x equal to x at the point c. Now in case of identity function, f of x is equal to x. So the limit becomes limit x approaches c, x is equal to c. So now in this case, the limit of the function and the value of the function at the point c are both equal to c. And as per the definition of continuous function, if the limit of a function and the value of a function at a given point are same, then that function is a continuous function. So that means the identity function on real number given by f of x is equal to x is a continuous function at every real number. Now let's solve one more question. Show that the function f of x given by f of x is equal to x into sine of 1 upon x, where x is not equal to 0, and f of x is equal to 0 when x is equal to 0 is continuous at x equal to 0. Now this function f of x will be a continuous function at x equal to 0 if its limit at the point 0 is equal to the value of the given function at the point 0. Now from the definition of this function, you can see the behavior of this function or the value of this function will be different if we move to the other side of x at the point 0. So let's first find the left hand limit of the function at x equal to 0. Now the limit x approaches 0 from the left hand side, f of x is equal to, now the limit of the function at x approaches from the left hand side means that the value of x is very close to 0 from the left hand side, or you can say the value of x is 0 minus h, where h is a very small number. So this limit can be also written as limit h approaches 0 f of 0 minus h, and which is equal to limit h approaches 0 f of minus h. Now putting the value of minus h in the function, as you can see, if x is not equal to 0, then in that case the value of f of x is equal to x into sine of 1 upon x. So in this case, now this limit becomes limit h approaches 0 minus h into sine of 1 upon minus h, and sine of minus theta is equal to minus sine of theta. So this is equal to limit h approaches 0 minus h into minus sine of 1 upon h, and which is equal to limit h approaches 0 h into sine of 1 upon h. So here we have to find the limit of a function which is product of two quantities, and the first is h and the another is sine of 1 upon h. And now, and you know it very well that sine of any angle is always between minus 1 and 1, as its minimum value is minus 1 and its maximum value is 1. So this limit can be also written as, now when h approaches 0, that means it's very close to 0, also it's equal to 0. So now this product can also be written as 0 into a number which lies between minus 1 and 1, and 0 multiplied by any finite number is equal to 0. So that means and the left hand limit of this function at the point 0 is equal to 0. So in the same manner, let's find the right hand limit of this function. Now the right hand limit at x equal to 0 is equal to limit x approaches 0 from the right hand side f of x, and again we can also write it as limit h approaches 0 f of 0 plus h, or limit h approaches 0 f of h. Now putting the value of h in the function f of x, and the value of the function f of x at the point h is equal to limit h approaches 0 h into sine of 1 upon h, and again this is equal to 0 into a finite number lying between minus 1 and 1, and which is equal to 0. So that means the right hand limit of this function is also equal to 0. And what's the value of the function f of x at the point 0? And as per the definition of the function, we already given that f of 0 is equal to 0. Now here in this case, the left hand limit is equal to 0 and the right hand limit is also equal to 0, and also both of them are also equal to the value of the function at the point 0. And from the definition of continuous function, you know it very well that a function is continuous at a point if and only its limit exists and is equal to the value of the function at that point. And in this case, the limit is equal to the value of the function f of x at the point 0, which we have already proved. So that means the function f of x is continuous at x equal to 0.